Okay. So molecular compounds continued. Hello. Sure. Okay, so just a little recall here. Molecular compounds are created when nonmetals bond together using covalent bonds to create discrete particles called molecules. Okay? So just a quick something to remember here is let's talk about something like this. Carbon tetrachloride. And we haven't gone over naming yet, but we will very shortly. So this is the combination of carbon with chlorine. Okay? So let's just remember what carbon looks like. Carbon has how many electrons in its outer shell? Did you hear that? Hold up your hand and show me on your fingers. Good. Carbon has 4 electrons on its outer shell. Perfect. Okay? And let's do this color. And chlorine has how many on its outer shell? Good. 7. Okay, and actually let's represent chlorines as little X's, okay? Just so we can remember where these came from. So if you look, it should probably almost be obvious that what's going to happen here is you're going to get 4 chlorines orientating themselves around the carbon, right? Such that they end up with this shared pair of electrons, okay? Now this is going to get a little bit filled up quick here, a little bit cramped, okay? But I think you can see now, if I start to circle the atoms, you'll notice that that shared electron from carbon fills out the shell for chlorine, and then each of the shared electrons that chlorine has shared fills out the electrons for carbon. So if you were to add all these up, 2, 4, 6, 8 around every chlorine, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, it's now stable, and 2, 4, 6, 8 around carbon. Okay? So what we would call this is we would call this thing, this bundle, a molecule. And if we were to interact with a tank or something of carbon tetrachloride, basically it would be a giant cylinder just filled with billions upon billions of these little units all bumping around and bouncing off one another. Okay? So that is a molecule, and that's a carbon tetrachloride molecule. Now, the way that we've drawn it here, okay, kind of has a name, and I don't know if this is an official name, but I like to call this a Lewis workup. Okay, so this is a Lewis workup. So what it's doing is it's keeping track of every electron and how it's involved in a bond. So I'm just going to point out here that we know right in here that each of these sort of areas where the circle converges on top of itself, that counts as a chemical bond or a covalent bond. I'll just write that into words in a second here. So this is the Lewis workup of the carbon tetrachloride molecule. Are there any questions about that so far? Does that make sense? Okay, I'll just take your silence as being that you're cool with that. So what I want to say is here is I want to say that a shared pair of electrons is, it has the name, it is a covalent bond. Okay, that's what it's called, and it's a very strong bond between these two elements. Okay, this is a pretty stable molecule and fairly unreactive, and these guys just sort of stick on there through this bond. And remember, it's a completely different kind of bond than an ionic bond. There's nothing really positive or negative here. We'll learn later that there's a little more to that story. But for the most part, right, it's a shared, the electrons kind of exist in between the two, and they're part of each shell, okay? So a shared pair of electrons is a covalent bond. It's also known as a molecular bond. It's also known as a molecular bond. One other thing I want to show you is oftentimes you don't see the entire Lewis workup. There's sort of a different way of writing this. So we can say that other than the Lewis workup, we can also represent molecules differently. We can also use the skeleton formula. To represent a molecule. Okay, and in the skeleton formula, lines represent the bonds or electron pairs. Okay, so I'm going to put a new heading. I'll talk quickly about the skeleton formula. So lines represent electron pairs. So let's look at what the skeleton formula of that particular molecule would be like. So we've got carbon in the middle, and carbon is bonded 4 ways to chlorine. Okay, and chlorine has unpaired electrons around it, right? So what we'll do is we'll draw those as little bars. Okay. So this still represents what we want to show. It's just a slightly different way of doing it. Okay. So this is the skeleton formula. Okay. And we'll just say what these are. So these represent electron pairs. Okay, and in this case, we call these unshared electrons because they're just, belonging to chlorine. And down here, where the line connects two elements, we call these bonding electrons. They're found within the bonds. Okay? So that's all there really is to the skeleton formula. It's a shorthanded way of representing all those electrons that we found in the Lewis diagram. Okay? You as students will be asked to be able to do both of those. Okay? Especially when you're just starting out. So if we just start, throwing this at you, sometimes you might lose track of where the electrons came from, and you might not completely understand why this forms the way that it does. Okay? Can we try one more? Okay, how about this? I'll give you guys one to try on your own here. Try to draw the Lewis and skeleton formulas, formulae, for water, which is H2O. Okay, so we're just going to take a pause there for a second. Okay, so let's look at this together in case anyone didn't get it. The first thing I would do is I would probably, draw out sort of what I'm dealing with. So 2, 4, 5, 6 electrons there. one each on the hydrogens. So you can see, okay, that would slot in nicely. I'll bring one, and I'll bring one. And then we have the 8, and then this shared pair will fill this shell with 2, right? So actually with water, it's kind of interesting. Actually is a bent molecule. Not that you need to know that, but you end up with this right here. And if we circle this, there's the 8 that oxygen needs to fill its shell. There's the 2 that each hydrogen needs. So there are bonding pairs and there are non-bonding pairs. So when we write it out, we get something that looks like that. If you wrote it in a straight line, that's fine. Okay? It doesn't really matter at this stage, but that's the basics of how you're going to do that, right? So just in case you're not exactly sure, these are non-bonding electrons, so that's that and that. Okay, and then in here, these are our bonding pairs, and that's this guy and that guy. Okay, are there any questions about that? Did anyone not get that? Okay, awesome. So now I'm almost done, but I want to talk about double bonds. Double bonds. So sometimes we need to share more than one pair of electrons. Dot, dot, dot. So let's look at one prime example of that. Today, we burnt a candle, and we said that one of the byproducts of burning a candle is CO2. Okay? So if we were to write out a molecule that looks like CO2, okay, just remember, right, this little subscript tells me there's 2 oxygens. No subscript means there's 1 carbon. Okay? So let's look at what we're dealing with here. So we've got carbon, and it's got 4 electrons around it. We have 2 oxygens, and each oxygen has 6. So if we look, each of these needs 2. Needs to add 2 electrons to its outer shell. And carbon needs to add 4 electrons to its outer shell. Okay? So at first that might seem totally impossible. Like, how can that ever be? Right? Ooh, so what we have to do here, we look, what if we were to take our carbons and do that, and we're to look at our oxygens. Now, oxygen has 6 in its outer shell. So if I do this right here, and I do this right here, and then I do my little circling that I've been doing, watch what happens. What you actually end up with is inside the covalent bond, you have 4 electrons, or 2 pairs. Okay? Now let's count around the oxygen. 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons. And around the carbon, 2, 4, 6, 8 electrons. Okay? So this actually has 2 bonds in each covalent bond. So this is the concept of the double bond. It's a double bond. And how do we represent that in a skeleton formula? Well, very similar to what you would expect. We have our carbon in the middle. We have 2 bonds with oxygen, and 2 bonds with oxygen. And then we have our leftover electrons hanging out like that. So there you go. This is the concept of the double bond. Does that make sense to people? Okay, a little challenge. Show Lewis and skeleton for O2, oxygen. Okay, let's just sort this out real quick. So if I look, 1, 2, 3, 4, 5, 6 on each oxygen. So each oxygen needs 2 electrons in order to fill its shell. You know, it doesn't really look obvious what's going to happen here. However, if we put our shells like this, and circle them up such that we're sharing 4 electrons again, you'll see that you have 8 around here, 2, 4, 6, 8, 8 around here, 2, 4, 6, 8, and you end up with those 4 shared electrons inside the bond. And its skeleton picture is going to look like that. Okay, so there's the double bond. And we're not quite done yet, because there's one more, and that is the triple bond. Oh yeah, the triple bond. Don't worry, that's as high as it goes. Triple bond's as high as it goes. Okay? And we'll just do this, you know, I mean, it follows the same pattern, right? So this is 3 pairs of electrons are shared for a total of 6 electrons. The classic example, there's a few more, but the classic example that's always used for this is the nitrogen molecule. Okay, so if I look at nitrogen, okay, it looks like this, and we'll memorize actually in a little bit here all the diatomic molecules, but this is another one, diatomic molecules that are elemental. Don't worry about that right now, but for now, nitrogen is N2. If I look, nitrogen has 1, 2, 3, 4, 5 in its outer shell, and each of these needs 3 electrons in order to have a full outer shell. Okay, so the way that nitrogen gets by is it's going to end up putting 1, 2, 3, 4, 5, 6, and we're going to have, so 2, 3, 4, 5. There's the 5 from this guy, 1, 2, 3, 4, 5. And the 5 from this guy, 3, 4, 5, like that. And if we go ahead and circle around this, circle around this, we see that now we've got our 8 rule satisfied, right? So 2, 4, 6, 8 on this nitrogen, 2, 4, 6, 8 on that nitrogen. And we have inside here 3 pairs. So skeleton-wise, yeah, just like you would expect, and then the 2 non-bonding pairs outside. So I'm going to ask you guys to try one for me. Show me how you can make a carbon monoxide molecule. Okay, so let's look at what we're dealing with. So we've got carbon, it's got 4. We've got oxygen, and it's got 6. Okay, so carbon needs 4 more. Oxygen needs 2 more. So what ends up happening here is carbon has 4, and oxygen has 6. So have a look. What's going to happen here, right, is carbon's going to borrow 4 from oxygen. Oxygen's going to borrow 2 from carbon. Do you see what happened there? Carbon borrowed 4 from oxygen because it needed 4, and oxygen only borrowed 2 from carbon. So if we draw our loops, we see 2, 4, 6, 8 around carbon and 2, 4, 6, 8 around oxygen. And There we go. We've made our triple bond and we've created carbon monoxide. See? Triple bond. Bubble. Does that make sense? Are there any questions about that? Yeah. Okay. Yeah, I'm not sure about the question. I'm just gonna stop this right now and then I'll try to answer that, okay?